Hello, everyone. Before we start, am I audible to all of you? You all can just type in the chat box if I'm audible or not. Can all of you hear me? Okay. And I'll be sharing my screen now. And after I share it, I'll ask you if the screen is visible. Is my screen visible? Yes. Okay. So during the session, I'll be stopping from time to time to ask you all if you all are still with me or if you have any questions. And when I ask that, if you have any questions or if you feel stuck anywhere, you can raise your hand and we'll unmute you. And sometimes I'll ask you to type in the chat box. Okay, so shall we start?
Yes, you can. And one more thing.
Yeah.
Whose name is Shravani and please rename yourself with batch, and Nidhi, you are also please rename your mention your batch name. Yeah, you can start now, Pranali. Thank you.
Okay. So hi, my name is Pranali and I'm also a student like all of you, learning new and interesting things in mathematics every day. And I'm here to share a few of the things I learned. So in this Saturday session and next Saturday, we are all going to have a lot of fun because we will be exploring something that most of us haven't looked at before. And there is a surprise waiting for you all because when I tell you the name of the topic we'll be looking at, the first thing that comes to your mind will not be what we'll be exploring. It's something very different. So let's see what you all already know. When I say the word graphs, what's the first thing that comes to your mind? You can type in the chat box the first thing that comes to your mind when I say graphs. Have you all looked at graphs before? Okay, Nidhi says bar graph. Sandhya says data. Medha also says bar graph. Graph sheet. Okay, so all of you all are right. We think of graph sheets, we think of bar graphs, line graphs, x-axis, y-axis when we say graphs. But there is another object in mathematics which is also called graphs, and it has got nothing to do with what we have looked at till now. It just has the same name. And these graphs that you all are talking about, bar graphs, graph sheets, line graphs, Cartesian plane, all of them come in an area of mathematics called statistics. These new graphs that we'll be looking at, these surprise graphs, come in an area of mathematics called graph theory. And it's a very, very interesting area because it helps you solve a lot of brain teasers. So when you all were small, you might have looked at these puzzles and brain teasers. You might have tried solving them, might have been unable to solve them. And graph theory helps you solve a lot of such brain teasers. So these new graphs that we'll be looking at, they consist of dots and lines. Nothing else, just dots and lines. And the lines always connect to dots. So in mathematical words, the dots are called vertices. Each individual dot is called a vertex. And the lines are called edges. So all the polygons that you know about, squares, triangles, rectangles, are examples of graphs because they have vertices and they have edges joining the vertices. And you all might have played a lot with polygons while studying geometry. But this time, although the whole session will be filled with dots and lines, we won't be doing any geometry on them. We won't find any area, we'll not find any angle. And even without using geometry, we'll show that dots and lines can be very, very powerful. And in fact, these graphs, which are made up by dots and lines joining those dots, are so powerful that they are used not only in mathematics, they are used in engineering, they are used in other sciences, in chemistry, biology, they are used in architecture, and lots of other areas. And the reason why these graphs, so this slide here has lots of graphs. The first one is this bluish green one. The second one is the one with yellow vertices. So I've added a lot of graphs on this slide. And the reason why these graphs are so powerful is that they offer a lot of choices to you. So if you go to a birthday party, if you have say 5 items on the menu, you might feel that the menu is not very useful. If you don't like all the 5 items, you'll stay hungry. But if you go to a party and there are say 50 items on the menu, then you are more likely to be happy and satisfied. So this area of graph theory is like a very huge food menu. It offers choices to almost every area, not only mathematics. And the reason is that it can be used to represent any real life situation. So I'll give you a very simple example. We'll use a graph to represent our class right now. So each vertex here in the graph can be one of you, can be one of the girls. So say one vertex is Diksha, one vertex is Mridula, one vertex is Nidhi, and so on. And I will join two vertices if those two girls are friends. If they are not friends, I will not join those two vertices. So say I look at the first graph on this slide, the top left one. Say the first vertex, you all can see my cursor, right? It's moving on the first vertex. Okay. So say the first vertex is Nidhi and this second vertex is Diksha, and Nidhi and Diksha are friends. So I will join them with a line. Say this vertex is Nidhi and this vertex is Mridula, and they are not friends. They do not know each other. So I will not join them by a direct line. Okay, so this is one real life situation that we represented with dots and lines. And there are lots of other situations. Say we have a city map, and on the city map, we will represent the houses in the city with the dots, with the vertices. And I will join two houses with a line if there is a road connecting them. If there is no road connecting them, I will not join them with a line. So say house 1 and house 2 are connected by a road. So I will draw a line joining those two houses. And if house 1 and house 4 do not have a road between them, I will not draw a line joining them. Now, even within these all representations, there are lots of choices. So say in some city, there is a one way, by which I mean that vehicles are only allowed to drive in one direction on the road. Then I can add directions to the edges. So if you look at this middle graph on the left side, it has arrows on the edges. So if I want to show the direction in which vehicles can move on a road, I can add arrows. Or if there is a road from one place to the same place again in a circle, then I can add a loop at that vertex. Or if there are more than one roads connecting two houses, I can draw multiple lines between two vertices. So if you look at the bottom right graph, there are two lines between two vertices. So that could mean that there are two roads connecting two houses. So there are lots and lots and lots of possibilities which could be represented by graphs. And then once you represent those possibilities by graphs, you can solve a lot of problems about them. And we'll be looking at one such problem, which in fact caused people to start studying graphs, to start graph theory. And it's a brain teaser. You might have seen it before in brain teaser books or somewhere else. And maybe that time you were not able to solve it, but now we'll be able to. So this problem, because of which people started taking interest in graphs, not the statistics graphs, the graphs with dots and lines, is called the Königsberg Bridge problem. And Königsberg is an actual place, and I think today it's in Russia. I'm not sure if the river is still there, but in the 18th century, there was a river flowing through Königsberg, and there were two islands in the river. So this picture here shows that there was a river flowing through Königsberg, and there were two small islands in the river. And people wanted to travel from one land area to the island, from the island to the other land area. So the people of Königsberg made bridges at that place. They made bridges for people to travel from the land to the island, from one island to the other island, and so on. And then they asked a question. So I'll tell you what was the question they asked. I'll annotate the PDF, just 1 minute. Yeah. So they asked that if a person stands anywhere on any of these land areas, say a person is standing on this island. Uh, Let me check if I can annotate it. Okay. So if a person is standing on this island, you all can see the person I have drawn. Okay. 1 second. So there is a person standing on this island and he wants to walk over each bridge exactly once. So he cannot retrace a bridge. He wants to walk over each bridge exactly once and cover all the bridges. So say he or she decides to start with this middle bridge. So the person will walk over this bridge first. Okay. And once the person has done that, this bridge is crossed out. You cannot walk over that bridge again. Now the person is here and has two choices. Could go from the top bridge or he or she could go from the bottom bridge. Say they decide to go from the bottom bridge. So they are going from here. Okay. So now you are on this land. And the question asked, can you walk over each bridge exactly once without retracing any bridge? And this might remind you of something you used to do when you were small. Have all of us tried to draw this square envelope kind of thing without lifting the pencil? You all have done that when small? When you were younger? Trying to draw this square envelope without lifting the pencil? You have, right? And even that question is going to get answered for you today. Why is it possible or why is it not possible is going to get answered today. And this Königsberg bridge problem is exactly the same. It's saying, can you walk over each bridge exactly once and cover all bridges without retracing your path? And did everyone understand the question? So say after this person reaches here, she goes through this on this bridge. Okay, then on this bridge. I'm just trying where I could go. Okay, and then coming back by this bridge, back on the island, and then on this bridge. But now this bridge is yet to be crossed. And the question said each bridge should be crossed exactly once. But now I have no way to proceed because I have already walked over this bridge and this bridge as well as this bridge, and retracing is not allowed. And we are not allowed to swim through the river, only walking on the bridges. So is the question clear to all of you? Walking on every bridge exactly once and not retracing the bridge. It's clear to all? You can type in the chat box.
Ask now.
Um,
The person start from anywhere or should they start only from the center?
they can start from anywhere on any of the land areas, not on the bridge, but on any of the land areas the person can start.
Okay.
I gave an example when the person started at the center, but the person could even start here. And from there, the person will have to travel over each bridge exactly once and not retrace any bridge, but every bridge should get covered once. Okay, is it clear to you now?
Yes.
Okay. So the people of Königsberg used to actually go there, try to walk over the bridges, see if they are able to do anything about it, if they can find such a path. But they tried for years and they failed. And in the end, there was a mathematician in the 18th century, and you all might have heard his name. His name was Leonard Euler. And you might have heard his name because he's not only there in graph theory, he has contributed to nearly every area of mathematics, number theory, geometry. He has even contributed to areas outside of mathematics, astronomy, physics, and so on. And he was the reason that graph theory as a subject started to be studied. He said that you all don't have to go to Königsberg and actually try it out. I can sit at home and tell you that it's not possible. So what Euler did is something very interesting. Euler assigned a vertex to each land area. So here there are a total of 4 land areas. This is the first one. This whole big land area from here to here is the first one. This island is the second land area. This huge bottom land area is the third one. And the remaining island is the fourth land area. He gave a vertex to each land area and he gave a line or an edge to each bridge. So to this land area, he gave a vertex, which is just a dot, gave a vertex here, vertex to the third land area, and vertex to the fourth land area. And he gave a line or an edge to each bridge. So this is one bridge. So he gave one line to this bridge. This is a bridge connecting land 1 and 2. So he gave one line to this bridge. Again, there is this bridge connecting land 2 and 3. So he gave one line to the bridge connecting 2 and 3. Another line to this one. And so on. So he also drew lines for the remaining 3 bridges. This one will connect vertex 1 and vertex 4 because it connects land 1 and land 4. This center one will connect 2 and 4 because the bridge connects land 2 and land 4. And the final one will connect 3 and 4 because the bridge connects lands 3 and land 4. So he converted this map into a graph. And let us see what he did after that. So this picture on the top here, top right, shows how he converted the map into a graph. He gave a vertex to each land area. So land A, land B, land C, land D. And he gave an edge or a line connecting the vertices for each bridge. And the graph is redrawn in the bottom. So when I go from vertex A to vertex C, say along this line, if I go from vertex A to vertex C along this line, that means that I went from land A to land C along this bridge. Or if I go from vertex D to vertex B along this line, it means that I went from land D, that is here on the top map, to land B, which is this land, along this bridge. So he did not change the problem. He just converted the map to a graph with dots and lines. And now the question is, if you can start on any vertex and trace the whole graph without lifting your pencil and without retracing it. So again, same as the square envelope shape which you used to try making. It's the same problem as that one because we want to walk over each bridge exactly once. So the whole diagram should get traced. Every bridge should get crossed. And we are not allowed to retrace. And we cannot lift the pencil and jump from one place to the other. So we need to walk in a continuous way. So if I'm here, I need to only walk over the bridges. I cannot jump from B to C. So is this problem clear to you all? How he converted this to a graph? How he converted the map to a graph? He took the lands as the vertices and he took the bridges as the lines. Okay, that's clear to all of you. Now next, what he did is, he said that now I'm going to only work with this graph. I have to trace this graph without lifting my pencil and without retracing any part of it. And he said that every vertex has 3 choices in all. The first choice is it could be the starting vertex. So when I drew my path in the previous slide, I had started on the middle land. I had started here. So I had started on vertex A. But that's not necessary. Like one of you asked, it's not necessary to start at the center. I could start anywhere. So the vertices, one of the vertices, say some vertex, say I choose C, is the starting vertex. SV is starting vertex, which means that I will start my journey on land C. Okay, so the vertices could either be a starting vertex or could be an ending vertex, by which I mean after I have traced the whole diagram, I'll have to stop somewhere. I cannot keep drawing. I'll have to trace the whole diagram without lifting my pencil, without retracing. And when that journey is over, I'll have to stop at some vertex. Do one of you have a doubt? Is someone on unmute? Okay. So the vertices could be a starting vertex or they could be ending vertices. So I say I start at C and I end my journey at D. Okay, so D is my ending vertex. which means I started walking from here. Say I crossed this bridge first. Then I came to A. Then I went to some other bridge, say this one, and I reach vertex D. Then again I'll leave from here and go to some other vertex. But in that whole journey, there will be some place I started and some place I end. And there could be only two such vertices, starting and ending. And in all, we have four vertices. So there will be at least two vertices which are not starting vertex and not ending vertex. So say if C is starting vertex, D is ending vertex, then we are not starting at A because we are starting at C, and we are also not ending at A because we are ending at D. So is this much clear to all of you? There will be two vertices where we do not start or end, because there are only two possibilities, starting vertex, ending vertex, and only two vertices can take that position. So if I give C this and I give D this, then A and B cannot be the vertices at which I start or end. Or if I give A this, I take A as the starting vertex in my journey, then C and D cannot be the starting vertex or ending vertex. So now, once we have that, since we know that two vertices will neither be starting vertex nor ending vertex, so say C is the starting vertex, and I'm starting my journey from C. So say I cross over this bridge and I reach A. Now I am not ending my journey at A. I have decided I'll end my journey at D. So every time, if I'm not ending my journey at A, every time I come at A, I will also have to leave from there, because I'm not ending my journey there. So it means that I'll have to come at A and also leave from there. So if you're traveling to, say, Delhi, and you first take, it's a flight which first goes to Pune and then to Delhi, then you cannot stop at Pune. Your journey ends at Delhi. So you need to even leave from Pune. So if A is a vertex you're not ending at, every time you arrive at A, you'll have to leave from there by some other bridge, because you are not allowed to retrace an old bridge. So say I leave from here and I arrive at C again. Then from there I can only use this bridge. Other two bridges are taken, they are already crossed. And I go to D. Now at some point, I will arrive at A for the second time. Okay, so say I arrive at A again. But again, when I come to A, I will have to leave, because I'm not ending my journey at A. It's an intermediate stop. So I'll have to leave. So notice that whenever I cross land area A, two bridges are getting striked out. The one I came by and the one I left by. And leaving is important because you are not stopping there. Your journey is not ending there. So two bridges are getting crossed out. The arriving one and the departing one, the leaving one. So this bridge got crossed out, this bridge got crossed out. Again, when you arrive at A for the second time, two bridges will get crossed out. The arriving one, this one, and the leaving one, this one. So at a time, two bridges get crossed out. But here A is connected to 5 bridges, odd number of bridges. So after you cross out two at a time, two got crossed out. The next time you arrived at A, total of 4 got crossed out. If there were say 2 more bridges, then the next time you arrive, more 2 will get crossed out, arriving one and leaving one. So at a time 2 get crossed out, and in total even number of bridges will get crossed out, because 2 at a time, 2, then next time you come 4, next time you come 6 get crossed out, and in the end 1 will remain because it's connected to odd number of bridges. Is this clear to all of you? You can just type yes in the chat box, and if you haven't understood, I'm ready to repeat. It's clear? Okay, very good. It's clear to all of you?
Ma'am, can you repeat?
Yeah, sure, I'll repeat. So I'm saying that I'll have to start my journey at some vertex and end my journey at some vertex. Vertex here are the land areas. I'll start on some land, and after my journey is over, I'll end at some land. So say I start at C and I end at D. So there can be only two vertices which can take the position of starting vertex and ending vertex. The remaining two have to be middle vertices. So if I'm starting at Mumbai and ending my journey at Delhi, if I'm traveling in the middle to Pune and then to Kolkata, I have to leave from those places because in the end I want to arrive in Delhi. So if I'm starting at C and ending my journey at D, whenever I arrive at A, I have to leave from there. Whenever I arrive at A from some bridge, I'll also have to leave from there by some other bridge because retracing is not allowed. I cannot take the same bridge which I took when I arrived there. It's like it's important for you to change flights whenever you are arriving at a city. So I came by this flight to Kolkata, but I need to leave by another flight because eventually I need to get to Delhi. Again, the next time I arrive at A during my journey, I'll have to leave again by some other bridge. So since you're not allowed to retrace a bridge, the option of crossing this bridge goes away. The option of crossing this bridge goes away for your future journey. This bridge goes away. This bridge goes away because you're not allowed to retrace any of the bridges. So whenever you arrive at land A, two bridges will get crossed out. The one you arrived by and the one you left by. Again, the one you arrived by and the one you left by. They get crossed out. So two get crossed out at a time. So every time you arrive at A, the first time you arrive, two got crossed out. The next time you arrive, four got crossed out. The next time you arrive, six got crossed out. So an even number of bridges will get crossed out from A. Is this clear to you?
Yes, ma'am.
Okay. So even number of bridges will get crossed out from A, but A is connected to 5 bridges, odd number of bridges. So one bridge is still remaining. We crossed out 4 bridges. And the question says that every bridge should get crossed exactly once. So I'll have to cross this bridge also at some point. So say at some point in my journey, I crossed this bridge. But my journey was not ending at A. I have not yet arrived in Delhi. I'm still in Kolkata. So my journey has not ended yet. I need to leave from here. But the all the bridges got crossed out. Even number of them, except this one remaining one, got crossed out because every time I came, I left. In the end, only one was remaining. All even number of them got crossed out. Only one was remaining. And once I walked that bridge, I'm stuck because I cannot leave from here. Even instead of 5, if it had say 7 bridges connected to it, 1, 2, 3, 4, 5, 6, 7. So if this is some landmass and it had 7 bridges connected to it, every time I come, I will leave because I'm not ending my journey there. So first 2 bridges got crossed out. Again, I arrive at the bridge, that landmass, and I leave. Again, 2 bridges got crossed out. Again, the same thing. Next time I arrive at that landmass, I again leave. More 2 got crossed out. So even number of them get crossed out. 2, 4, 6. And in the end, 1 remains. If there are odd number of bridges attached to it, 1 will remain. And when I cross that bridge to arrive at that land, I have no way to get out because all my bridges have crossed out. So I'm stuck and I'm not ending my journey at A. So is this part clear to all of you? You can type yes in the chat box. Okay, very good. So Euler said that if any vertex has odd number of bridges attached to it, you have to either end your journey at that vertex or start your journey at that vertex. Because if it's a middle vertex, it will cause a problem. Every time you arrive, you'll have to leave. When you do that, even number of bridges will get crossed out, and in the end, 1 will remain. And you cannot walk over that because you will get stuck the way we showed just now. So Euler said at a time in any graph, only 2 vertices can have odd number of bridges attached to them. So that one of them can be given the starting vertex, the other can be kept as the ending vertex. So here, if D is the starting vertex, it's not going to cause a problem because it has odd number of bridges attached to it. Because if it's the starting vertex I'll start my journey. When I start my journey, one bridge will get crossed out. And since it was connected to odd number of bridges, after crossing out one bridge, even will remain. And since even number of them remain, whenever I arrive, I can leave. So that won't cause a problem. Or if I'm ending my journey at D, again, it won't cause a problem. Because every time I arrive at D, I leave from D till only one of them remains. Even number of them will get crossed out, 2 at a time. In the end, only one will remain. But since I'm ending my journey at D, when I cross that bridge, my journey is over and I have crossed all bridges. I don't have to leave from here again. So this is like my Delhi. Once I reach there, I don't have to leave from there. So only 2 vertices have the choice of being connected to odd number of bridges. The starting one and the one at which you end your journey. Other vertices have to have even bridges connected to them, because whenever you arrive, you'll have to leave. If they have odd number of bridges, you arrive, you leave, you arrive, you leave, even number will get crossed out. In the end, one will remain. And that will cause an issue. And that's why in this graph, this Königsberg problem graph, it's not possible to trace the whole diagram or to cross each bridge exactly once without retracing, because if you notice, all of them have odd number of bridges attached to them. C has 3 bridges, D has 3 bridges, B has 3 bridges, and A has 5 bridges. All are connected to odd number of bridges. So if one is starting and the other is ending, there will still be 2 remaining with odd number of bridges attached to them, and you cannot end your journey there. So you will be stuck. In the end, one bridge will remain. So is it clear why Königsberg bridge problem cannot have a solution? Why you cannot have such a journey?
Yes, ma'am.
Okay. So Euler was very smart.
Please repeat the last part.
Yes, sure. Which part, till where was it clear to you?
Yeah, after you said the initial point and starting point.
Okay. So there will be one initial point and one ending point, and any other point which is not initial or ending will have to have even number of bridges attached to it, because whenever you come, you will have to leave. So 2 at a time. If there are odd, one will remain, and when you come there, you cannot leave from there. You'll be stuck. That is the idea. So here, if you give starting and ending vertex to any 2 of them, say C is starting and D is ending, then there will be 2 left with odd bridges. A has 5 bridges, B has 3 bridges. So, and they are not allowed to have odd number of bridges, because whenever you arrive, you leave, you arrive, you leave, and then one extra will remain. And if you cross over it, you cannot leave because all other bridges have been covered. Similarly for B, if you arrive, you leave, one bridge remains. And when you cross over it, you are stuck because you cannot get out from anywhere. Is it clear now?
Yeah, it is. Yeah.
Okay.
So only starting and finishing point can have odd number of
Yes,
bridges.
yes.
Yeah.
So only beginning and ending one can have odd number.
Hello, madam.
Did anyone say anything? Okay. So only the beginning and the ending ones can have odd number of edges, but the middle ones cannot. The middle, Kolkata, Pune, everywhere else you're stopping while going from Mumbai to Delhi cannot have odd number of edges, because whenever you come, you have to leave. So 2 at a time have to be there. 2, 4, 6. They can have even number of edges, but not odd number of edges. And in this graph, that's not happening. So Euler said that in this, no matter how much you try, you're not being able to find a path such that you cross each bridge exactly once without retracing. So he was very smart. He sat at home and he gave the solution without actually going to Königsberg. And now you can go back to the problem you used to try when you were small. You used to try making this square envelope without lifting your pencil and without retracing any part of it. This is the same problem. There is nothing different about it. So say I start on this end. So that's same as starting on this vertex. I've just drawn the graph of that envelope here. So you start somewhere and then you trace some path. Say I trace this line first. So this is my starting vertex, and I'll end my journey somewhere. I can either end it at the same vertex or some other vertex. Say I end my journey here. So this is my ending vertex. So after I've decided where to start and where to end, two more vertices remain. And since I'm not ending there, whenever I arrive, I have to leave from there. And then one will remain. And when I arrive there, I'm stuck because all the three possibilities have gone out and I cannot end my journey here. My journey ends here. So here it's again the same idea. At like maximum of two vertices will get the tag of starting and ending. It's possible that the same vertex is the starting vertex and the ending vertex. But maximum two can have the tag of starting and ending. Then two more will remain, which have odd number of bridges attached to them. So every time you come there with your pencil, you will have to leave from there while tracing the diagram. And one extra line will remain. And when you trace that line with your pencil, you are stuck because you are not ending your journey there and you need to leave from somewhere. So that's why you are never able to trace this diagram without lifting your pencil. And I remember when I was in school, some people used to cheat while doing this. They used to bend their paper and do something. But that's a different topic. They are doing that by cheating. But if you do it honestly, if you try tracing it out on paper, you are always going to get stuck. Okay, so now this remained and I cannot retrace. So is it clear why this did not work when you used to try it out? Because all of them have odd number of bridges attached to them. So whenever your pencil comes at them, they have to leave if you are not ending there. And hence you used to get stuck. So did you get the answer of why it was impossible to draw this? Okay,
Yes.
so one of you all have asked a question in the chat. What if all the points have even ways? Is it possible? That's a very good question. So we will look at this next example that's there in the middle. Now it's an envelope with a handle. Like it's not just the square envelope. Now I've added a handle at the top. And some of you might have tried this variant also. You might have tried tracing this diagram without lifting your pencil. And you might have noticed that it is possible. So what was the secret there? I will first count the number of bridges it's attached to. So say this is vertex 1, this is vertex 2, this is vertex 3, and this is vertex 4. 1 is attached to 4 bridges. So even number of bridges. 2 is attached to 4 bridges. 1, 2, 3, and 4. So again, even number of bridges. 4 is attached to 3 bridges. And even 3 is attached to 3 bridges. And what had I said? Only the starting and ending vertex can have odd bridges attached to them. So I'll choose my vertices wisely. Because 4 has odd number of bridges attached to it, I will take it as a starting vertex. And even 3 has odd number of bridges attached to it. So I'll take it as ending vertex. So that my middle vertices, the Punes and Kolkatas from where I have to leave whenever I arrive, have even number of bridges. So they won't cause any problem. And let's check if that actually happens. So I start my journey on this vertex 4. I go along the diagonal. I'm tracing the diagram without lifting my pencil and without retracing any part. I arrived at 2. When I arrive at 2, I'll have to leave from there because I'm ending at 3. So say I leave along this one. So I arrived and I left from 2. Now I arrived at 1 and I left from 1 because I'm not ending my journey at 1. So I arrived and I left. Again I arrived at 2 and again I have to leave from 2. But this time I do have a path. And this was possible because it had even number of bridges. It had 4 bridges. And since it had 4 bridges, I could do arrive, leave, arrive, leave. And now I am at 3. Once I arrive at 3, say I go along the diagonal. And I reach 1 again. Again, when I reach 1, I leave from there. I can leave from here. Again, it had 4 bridges. So arrive, leave was possible for the bridges. And I arrive at 4. Now, finally, from 4, I leave. and I reach 3. Now even 3 had odd number of bridges attached to it. So once I arrive here, I cannot leave now. But that's not a problem because my journey is over. See, I traced the whole diagram. I did not lift my pencil anywhere. I traced the whole diagram without lifting my pencil. And that was possible because I'm ending my journey at 3. I don't have to leave now. So only the starting vertex and ending vertex can have odd number of bridges. Others need to have even. So since one of you all asked, is it possible if all points have even number of bridges attached to them? Yes, it is possible. And it's also possible if maximum two vertices have odd bridges attached to them, because then those two vertices can be chosen as the starting vertex and the ending vertex. And once those two are decided as starting and ending, remaining will have even degree and they won't cause a problem, like in this middle diagram. Towards the middle diagram, why is it possible to trace? Was that clear to you all? Just type a yes in the chat box. Okay. Okay. Okay, it was clear to all of you. Now I want you all to count the bridges attached to each vertex and tell me if the third diagram here, which is this square envelope with 4 handles, whether it can be traced without lifting your pencil and without retracing any part. Okay. Sandhya says no. He says no. No. Very good. So now you know how to look at the diagram that is given to you and tell if it can be traced or cannot be traced without lifting the pencil. And yes, this cannot, because each vertex is connected to 5 bridges. 5 is odd, and only the starting and ending vertex can have odd number of bridges. The remaining 2 will also have odd. So you will get stuck at some point. So the next time someone gives you some diagram made up of straight lines and asks you to trace it without lifting your pencil and without retracing, you can just look at the diagram. You can count the number of bridges at each vertex. You just draw a vertex at each corner and count the number of bridges that each corner is connected to. And you argue that no, it's not possible if there are more than 2 vertices with odd number of bridges.
Ma'am,
Yes.
ma'am, if we have one vertex with odd number and other 3 vertex with even number, so then, ma'am, then
Yes.
it will be?
Yes, it can be possible, because the one which had odd number, you can take it as the starting vertex and you can decide that you'll also end your journey there. It's possible that I start at Mumbai, I go to Kolkata, I go to Delhi, then I go to Pune, then I come back to Mumbai. So it's possible that I start my journey at some vertex and I end my journey also at that vertex. So if some vertex, okay, so say your question is that one vertex has odd degree. So say this vertex has odd degree and others have even degree. That's a good question. So this has 4, this has, okay, this already has 4. So I will not tamper with them. I'll go to the other one. Okay, so say this one has 4. This one, okay, wait, yeah, this one has 4. This one has odd 3 and these two also have 4. So since this has odd, I need to start my journey there or end my journey there. If I start my journey there, then one bridge will get crossed out. And now after one bridge gets crossed out, even number of bridges are left with it. So whenever I come at that vertex again, either from this one or from the vertical one, I'll have to leave from there because one bridge is yet to be covered. So I cannot end my journey here now because even number are remaining, and every time I arrive, I will leave to cover 2 at a time. So I cannot end my journey there. So say I end my journey at this vertex, top left vertex. But every time I arrived there, I left from there. Again, the next time I arrive, I'll have to leave because it has even number of bridges attached to them. So when I arrive, I leave, I complete 2. Next time I arrive, I leave, I complete 4. And if there are even, I need to leave every time I arrive. Arrive, leave to cover all the bridges. So no, it won't be possible. It was a very good question. And did you understand why it won't be possible? Like if the one which has odd number of bridges, you'll have to start there because only the starting and ending can have odd number of bridges. So you have to start and end at this vertex because this has odd number of bridges. And the problem is that when you start at it, one bridge gets crossed out and only even number of bridges remain. So you cannot end your journey here because since there are even number of bridges, whenever you arrive, you will also have to leave to cover 2 bridges at a time. If there were 2 more, then whenever you arrive, you'll also have to leave to cover those 2 bridges. So for your question, no, it won't be possible if one has odd and all the remaining have even. Was it clear to you?
Yes, ma'am.
Yes, and you can actually make more diagrams, not only with 4 vertices, you can have more vertices. You can try out the different possibilities. So we already saw the possibility of more than 2 having odd bridges. Now, the question which was asked right now was a very good one. If only one has odd, remaining have even, is it possible? And we saw that it's not possible. You may ask more questions. You may ask, say,
Ma'am, if we have all the vertices with even number.
okay, we have all the vertices with even numbers. So say, I'll clear the existing drawings first. Okay. So this one has 4, this one has 4, and say even this has 4, this has 4. So I'll start somewhere. Now,
Ma'am, if we connect them with other vertices, then they have 5 wells or bridges.
like, are you saying we add more vertices and attach lines to it?
No, ma'am.
Then
You leave them.
Ma'am, we can connect the bottom 2 vertices together, right, with a line. That will make it 4.
okay, okay. So you're saying we take this graph.
Yeah, so that will make
Okay, so let's look at this graph and say I start at some vertex. It doesn't matter where I start because it's very symmetrical. They all look the same. So say I start here, top left. This is connected to even number. All of them are connected to even number of bridges. I start here. Say I go horizontally like this. And since it was connected to even number of bridges, after I walked over one bridge, the one I started my journey with,
No, I think
that
it would be
got crossed.
possible.
Okay, let's see, we'll check. Okay, so that one will get crossed out. So now it's left with odd number of bridges. Once you start your journey on one bridge, it's left with odd number of bridges. So since it's left with odd number of bridges, you'll have to end your journey there because whenever you arrive, you leave, 2 will get crossed out. So in the end, 1 will remain. So you'll have to end with that bridge. So now you know that this should be the ending vertex. So you know that the starting vertex and ending vertex should be the same because when you started your journey here, 1 got crossed out, odd number of bridges remain. So whenever you come, you have to leave. 2 will get crossed out at a time. So the one odd one has to be ended with. Okay, so that we know now. So say I start from here. This bridge got covered. Now I am here. Now when I know I'm starting here and ending here. So all other are intermediate vertices. And all of them have even bridges connected to them. So that's not a problem. I come and I leave from here. 2 got covered. Again, when I arrive at the bottom left one, I leave. So 2 are getting crossed out at a time. And that's not going to cause any problem, I feel. Let's see. I reached here. So I came here, then I went down. I arrived and left. Here I arrived and say I leave from here. I arrived. Okay, I leave from here. I arrived like this and I left from here. So now I arrived on this vertex. I need to leave because I'm not ending my journey there. So say I leave from here. And I reach here. And then say I go, I have two choices. I go from here, the handle. I arrived here. I leave from here. I arrived at the bottom one. I can leave from this handle. And finally, I arrived at this bottom vertex and I can leave from this vertical one. And I reached at the ending vertex, which was same as the starting vertex. So yes, it is possible. And the reason it was possible is the starting vertex had even number of bridges attached to it. When we started our journey, one bridge got crossed out because you cannot retrace. So it was left with odd number of bridges. So you need to end your journey there. Because when you arrive, you leave. Two will get crossed out. In the end, you need to end your journey there. And remaining, all of them had even degree. That is, even degree is the number of bridges it's attached to in a graph. So remaining them were connected to even number of bridges. So whenever you arrived, you could leave. So it did not cause any problem. Was this clear to all of you? If you did not understand, I can repeat it.
Ma'am,
Yes, ma'am.
Yes.
is it possible to have the endpoints as even numbers?
Endpoints as we just saw, right? Like this diagram that we did just now. Let me clear the drawings once. We looked at this square envelope with two handles. In that, all of them had even. So the one which we started with had even 1, 2, 3, and 4. And it was possible to trace it because we picked the same vertex as the ending vertex. So I started here and I ended my journey there. So it is possible. Is it clear now?
Yes, ma'am.
So the next time someone gives you some diagrams, you can analyze like this. When would it be possible? When would it not be possible? And now you know for sure that if more than two vertices have odd number of bridges, then it's not possible. Because only the starting and ending one can have odd number of bridges. So let us move ahead. Now this is another brain teaser and the whole session is just filled with brain teasers because graph theory is full of them. So this next problem asks that if there are 15 telephones and I want to connect them with wires such that each telephone is connected to exactly 3 other telephones. This word exactly is important. It means that a telephone cannot be connected to 4 telephones. It cannot be connected to 2 telephones. It should be connected to exactly 3 other telephones. And the question asks if such a connection can be made. And this again, if you just keep trying it out, you buy 15 telephones, you try making such connection. If it's not possible, you'll keep trying and trying and trying, the way people of Königsberg used to try walking over the bridges, and you'll never succeed. But not succeeding is not a proof that it's not possible. You should give some logical argument as to why will it be possible or why will it not be possible. So again, this problem can be converted to a problem in graph theory by converting it to a problem in dots and lines. And notice that we are not doing any geometry with these lines and dots. The way we find the area or the angle to do some analysis, we are not doing that here. We are just using logic with dots and lines, like in the previous problem. And here again, we have 15 telephones. So I will take 15 vertices. Each vertex is a telephone. So this is vertex 1 is telephone 1, this one. Vertex 2 is telephone 2. Vertex 3 is telephone 3. And I have all the way up to vertex 15, which is telephone 15. Now the problem says that each telephone has to be connected to exactly 3 other telephones by wires. So I will take the edges of the graphs or the line in the graphs as wires. So say telephone 2 and telephone 12 are connected by a wire. So I'll draw a line between them. And suppose telephone 2 is connected to 10, 11 and 12. It should be connected to exactly 3. So one possibility is it's connected to 10, 11 and 12. So I'll draw a line, that is a wire connecting 2 and 12, 2 and 11 and 2 and 10. And say telephone 3 is connected to telephone 13, 9 and 8. So I will draw a wire connecting 3 and 13, wire connecting 3 and 9 and wire connecting 3 and 8. Now once I've connected 2 and 12, 12 has to be connected to 2 more vertices, because what does the question say? Each telephone is connected to exactly 3 other telephones. So right now 12 is connected to 2, but 12 needs to be connected to 3 telephones and all. So maybe it's connected to 5 and it's also connected to 6. That's one possibility. So it's connected to 2, 5 and 6. And there are lots and lots and lots of possibilities for you to decide which 3 telephones 12 should go or which 3 telephones 2 should go. But for now, let us assume that it is possible. Okay, I'm going to assume that it is possible and that the complete diagram with 15 telephones and all the wires has been drawn in front of me. Does anyone have a question?
I didn't understand it.
You did not understand what the question is asking?
No, how the connection is made.
Okay, so I'll explain again. We are just taking each telephone as a vertex. Okay, so telephone 1 is this circle, this first vertex. Telephone 2 is this circle number 2, vertex 2. Telephone 3 is vertex 3. This vertex means the circle, the dot. And telephone 15 is the 15th vertex. Is this clear to you? We are taking vertices as telephones.
Yes.
And if 2 telephones are connected by a wire, I will draw a line connecting them. So if telephone 2 and telephone 12 are connected, I will draw a line connecting 2 and 12. If telephone 2 and telephone 7 are not connected by a wire, I will not draw a line between vertex 2 and vertex 7. Is this clear?
Okay.
Okay, so that's how we are making the diagram. Whenever there is a wire connecting 2 telephones, we just draw a line connecting those 2 circles. So if telephone 3, telephone 13 are connected, we draw a line joining 3 and 13. And in the end, the connection should be such that each vertex, each circle is joined by a line to exactly 3 other circles. Not more, not less, because each telephone is connected to exactly 3 other telephones. So I want this telephone 3 to be connected to exactly 3 other circles. I want circle 5 to be connected to exactly 3 other circles, and that way for each circle. And I am asking if such a graph or such a connection can be made. And we'll see now that it is not possible. And even this argument is very nice, and it's a very common way to solve a lot of brain teasers. So now let us assume that it is possible and that connection has been made and it's kept in front of me. So I'll do something. I'm going to make X's on this, the letter X, and I'm going to make it at specific locations. I'll tell you where I'll make them. I'll make 2 X's on each line. Each of these lines joining 2 vertices, I will make 2 X's. One near one end vertex and the other near the other end vertex. So I made on this line, I made an X near 12 and I made an X near 2. Because it's joining 2 and 12, so I made an X near 12 and I made an X near 2. If I pick this line, then it's connecting 3 and 9. So I will make an X near 9 and I'll make an X near 3. This next line is connecting 3 and 8. So I'll make an X near 3, another one on this line, and I'll make an X near 8. So is it clear to all of you how am I making the X's? I'll take another example. 3 and 13 are connected with this line. So on this line, I'll make an X near 13 and I'll make an X near 3. Is this clear to all of you? How have I made the X's on the lines? You can type yes in the chat box. Whenever a line is joining 2 vertices, I make 2 X's on it. One near the one end vertex, the other near the other end vertex. So this is simple. Now these x's are going to be very powerful. I'll tell you why. So once I have made all the x's, now I haven't made the complete diagram here, but assume I have, and I have made all the x's. So there will be one x here, another one here, one x here on this line, and another one here. Can you tell me how many x's will there be near each vertex? I know that from each vertex, 3 lines are leaving because it's connected to exactly 3 telephones. And the x's are only made near the ending of the line. So near each vertex, again from 5, there will be 3 lines leaving because it's connected to exactly 3 other circles. And I will be making x's on the end of each line. So can you tell me near each vertex how many x's will there be? Okay, Mridula says 3, Nidhi says 3. And 3 is correct because exactly 3 lines are leaving from the vertex and we are making an x on each of those lines. So that's right. So in total, vertex 1 has 3 x's close to it, vertex 2 has 3 x's, vertex 3 has 3 x's. So in all, how many x's do I have? I have 15 vertices and yes,
45x.
yes, 45 x's. Okay, so the number of x is 45 because I have 3 near each vertex. Now I do not want to count the x's this way, so I'll count it in a different way. Let me ask you one thing. How many x's does each line have? I have on each line, I have made one x near one end and another x near its other end. So how many x's does each line have? Okay, Nidhi says 2.
2.
2. Perfect. So every line has 2 vertices and there will be some number of lines. There will be some n lines. So this is first line, this is the second line, this is the third line, fourth line, fifth line, sixth line. The total number of wires I have used while making the entire connection. There will be some n lines. I cannot have half a wire. Like I cannot start from telephone 6 and just leave the wire in the middle. I'll have to connect it to something. So in all, there will be some n, either 3 wires, 4 wires, 5 wires, 6 wires, 20 wires, 30 wires. There will be some number of wires in this connection. So say there are n wires and each wire has 2 x's on it. So how many x's are there? If there are n wires and each wire has 2 x's.
2n.
Yes, 2n. That's simple. So there are 2n x's in all. But when we counted it this way, when we said that each vertex has 3 x's close to it, so there are 3 into 15, 45 x's, and we got 45. And here we are saying there are 2n x's. So that means that 2n should be equal to 45. And what is n? N is the number of wires. It can be 3 wires, 4 wires, 5 wires. It has to be some natural number. But here if 2n is 45, n will have to be 22.5. We cannot have 22 and a half wire. We have some whole number of wires. So that means that such a connection cannot be made because then we'll have to have a half wire. And that wire won't connect any two telephones. So was this clear to all of you why such a connection cannot be made?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So now you can solve any problem which is of this sort, you'll be able to solve it now. If you have been given odd number of circles and you have to connect each of them to odd other number of circles, like here there were 15, which is odd, and you had to connect each of them to 3 others, which 3 is also odd. So in such a case, it wasn't possible. Now, after the session, you can think about more problems. You can ask yourself, say I had even number of telephones, would it be possible then? Or if each telephone was connected to 4 other telephones instead of 3, would it be possible then? So you can ask such questions. When will it be possible? When will it not be possible? Okay, Sandhya, I said, can you explain it again? Sandhya, at what part like were you stuck? Which part did you not understand? You can either unmute and speak or you can type. Last part. Okay. Um, did you understand how we made the x's? How we made the x's on the lines? We made on each line, we made one x near one end and the other x near the other end. So the reason this connection is not possible, one second, let me annotate it. The reason this connection is not possible is because if we count it as two crosses on each line and we have n total number of lines, some number of wires we have, and each wire has two x's, then we have 2n total x's. So this is one way of counting it. Other way is each wire has an x near its end. And each circle is connected to exactly 3 other circles. So there will be 3 lines leaving from there. And each of them has an x. So near each vertex, we have 3 x's. And we have 15 vertices. So we have 3 into 15 x's, which is 45. So 2n, which is the first way of counting, should be equal to 45, which is the second way of counting the x's. The number of x's haven't changed while changing the way of counting them. So then n will be 22.5, but we cannot have half a wire. Every wire is connecting one telephone to the other. So it's not possible. Was it clear now? Okay. So now we know that this connection cannot be made, but you can ask more questions. You can ask, instead of 15, if I had 16 telephones, would it be possible? Or instead of connecting it to 3 other telephones, if I connect to 4, okay. Like you can try it out on your own, and if you feel stuck, you can ask in the next session, because we'll be continuing with brain teasers next time. So before like deciding on something, try it out, like make 16 telephones, see if you can make such a connection. If yes, argue why can it be made. If not, you can argue why can it not be made. You can play with these kinds of problems after the session, or yeah, ask.
Ma'am, I tried 15 telephone with connecting 4 other telephone. I can't.
You
Means
yeah,
it will not happen.
okay, let's see. So we have 15 telephones. Let's see if the same argument can work to argue if it's not possible. We have 15 telephones and we are connecting each telephone to 4 telephones now. So 2 will have to be connected to 4. 3 will have to be connected to 4 in all. So this wire will go somewhere. It may join 7, it may join 8, anywhere. And I'll again make 2 x's on each line. When I do that, near each vertex, I'll have 4 x's this time, because each circle is connected to 4 other circles. And I have 15 circles. So I have 4 into 15, that is 60 x's. And the other way of counting the x's was some n number of lines. So I want 2n to be equal to 60 this time. So n can be 30. So now I need to check that by 30 wires, using 30 wires, can I make such a connection that each is connected to exactly 4? And that you'll have to try out. Now you know the number of wires you have to use. You need to try out the possibility or try making such a connection. And that you might not be able to do easily. You'll have to sit and draw. So you'll have to start from 3, connect it to 4 others, then connect the rest of them to also like exactly 4 other circles. It will take time. You cannot do that quickly. Okay, you'll try it after the session. You know that you need 30 wires now. Now you need to decide how to connect it using the 30 wires. But this argument cannot be used here to say that it's not possible, because 30 wires is possible. 22.5 wires wasn't possible because you cannot have half a wire. Okay.
Ma'am, can we do 30 divided by 4 and decide?
No, we cannot do 30 divided by 4 because we are not saying that every vertex is connected by a unique wire. Like it's possible that, like in the diagram that I have drawn, let me clear all the drawings first. You cannot simply do 30 divided by 4 because now here if you look, 2 and 12 were connected by this wire. Then say 12 is connected to 4, 12 is connected to 5. And since I'm connected to 4 other telephones, 12 is connected to 6. And 2 is connected to 10, 11, 12. And say 2 is also connected to 13. Then this wire, which is connecting 2 and 12, is common to 2. It's over here also. And it's also common to 12. When will that 30 divided by 4 make sense? When each vertex has unique 4 and that is not shared by anyone else. So you are sort of trying to give 4 to each of them. But here they are also sharing wires. This wire is shared by 2 and 12. This is shared by 4 and 12. So 30 divided by 4 won't make sense here. Division makes sense when you are giving n number of them to each of them. Then you are saying that you are dividing the quantity. But here the wires are shared between them.
Then can we do 30 divided by 4 into 2?
Oh, you're saying 30 divided by 4 into 2. No, you cannot. Like it won't make sense because when you're saying divided, this quantity is not making sense. Because you are not firstly giving 4 wires uniquely to each one of them. They are sharing that with other vertices. It's like if I want to divide 10 chocolates among 10 people, or say 30 chocolates among 15 people, then it's possible I give 2 to each one of them. But if I'm giving one chocolate to be divided between 2 people, then I cannot say that I gave 2 to each one of them. Like, are you understanding what's happening here? Like this wire is like a chocolate and this is one person. This is another person. And this wire is being shared by both of them. Similarly, other wires are being shared between 2 people. So it's not like 30 is being divided into sets of 4 to be given to each one of them. They are sharing the wires. Okay? Like if I would, okay, so it's like say this is person 1, person 2, person 3 up to person 30. And I'm saying that, okay, no, this is chocolates. So chocolate 1, chocolate 2, up to chocolate 30 I have, and I have 4 people. So it's not like I'm exclusive or I have 15 people. And it's not like I'm exclusively giving 4 chocolates to this person, 4 chocolates to the next person, 4 chocolates to the next person. It's not like that. They are also dividing the chocolates. Each wire, each chocolate is getting divided between 2 people. So it's not that simple. You cannot simply do 30 divided by 4. You'll have to think more on it. And in the case of 15 telephones with each connected to 4 others, I think it will be possible with 30 wires. I'll try making the connection and showing it to you next time. But in the meanwhile, even you can try it out. Okay. The only time it won't be possible is when there are odd number of telephones and odd number of connections. Okay. Is it clear to all of you? Okay.
Yes, ma'am.
Okay.
Yes, ma'am.
And after the session, make sure to try it out with other number of telephones, other number of connections. It's fun to try these things out. Okay, so now the third set of problems, we'll just look at the idea of it because we have only a little time left, but we'll be carrying this forward to the next session. And these set of problems are problems in chess. If you do not know how to play chess, if you do not know how the pieces move, do not worry. We only need to know how the knight moves on the chessboard, and I'll be explaining how it moves. And these problems were given by a mathematician named Guarini, and he was also an architect. So he had a liking for positioning things on paper. And that's why he came up with these problems. he used to ask that if I have a 3 by 3 chessboard, the actual chessboard is 8 by 8. It has 8 squares along a column and 8 squares along a row. But he picks a smaller chessboard. He picked a 3 by 3 chessboard and he put some knights on it. And the knights move in a certain way. Knights usually move in an L shape. So if this is a the black circle represents a black knight, the L need not necessarily be like the L we draw. It need not be this perfect L. It can be an inverted L. It can look like this, or it can look like this, or like this. But the shape should be an L shape, which means it can move one step to the side and then 2 steps below. It's always 1 followed by 2 or 2 followed by 1. Or it can move 2 steps to the top and 1 square to the right. Or 1 square to the top, 2 squares to the left. That way. So if I want to move this one now, I can move 1 square to the left and then 2 squares down. That is one possibility and it will arrive here. So is it clear to all of you how the knight moves on the chessboard, even to those of you who haven't played chess before or haven't seen a knight before? It moves in L shape on the chessboard. If it's clear to you, you can type yes in the chat box. And if you haven't understood how the knight moves, then you can ask me. Okay, it's clear to all of you. And all these problems given by Guarini need is knowing how the knight moves on the chessboard. Nothing else is required, just that and little bit of logic. So we have a chessboard, 3 by 3 chessboard, and Guarini has placed 4 knights on it. He has placed 1 black knight on the top left, 1 black knight on the top right, 1 white knight on the bottom left, and 1 white knight on the bottom right. And he says that I want to start moving these knights using the movement of the knights in L shape. So maybe I can move the black knight on the top left to the middle of the bottom row. I can move the white knight in the bottom left to the middle of the top row. So I can keep making such movements to the knights on the chessboard. Can I eventually reach this positioning where there is a white knight on the top left, white knight on, oh yeah? Does anyone have a doubt? Okay. So I think one of you all is on unmute. So the question asked, if we have these positioning of the knights, can we move the knights step by step? So I first move this black knight, then I move this white knight, and so on. Can I eventually reach this positioning? Finally, after all my moves are done, can I reach a board where the white knights are on the top left and right corners, and the black knights are on the bottom left and right corners? So they have swapped places. The top has come to the bottom has come to the top. And can this positioning be achieved by any sequence of moves? Is what Guarini asked. So here, first the chessboard looked like this: black on the top corners, white on the bottom corners. After I moved this black knight in an L shape, the positioning looked like this: white, black, white in the bottom, and 1 black knight at the top. I can again make a change. I moved this white one and I arrived at this new positioning. And can I keep making such moves so that I eventually reach this positioning where the white are on the top corners and black are on the bottom corners? Is what Guarini asked. And again, these problems, people used to actually make a small chessboard. They used to try it out and were not able to do it for a long time. In some cases, sometimes they could, and they couldn't give a logical explanation as to when will it be possible or when will it not be possible. And graph theorists came up with a solution to it. And they did it very smartly. What they did is they looked at the 3 by 3 chessboard. I've made it on the top left. There is a 3 by 3 chessboard. They numbered each square. So they gave this square number 1, the next square number 2, the next square number 3, and in all I have 9 squares. And they gave a vertex for each square. So this first vertex in the graph below it, the first circle, which is numbered 1, vertex 1, represents square 1 on the chessboard. Then vertex 2 represents square 2 on the chessboard. Vertex 7 represents square 7 on the chessboard. And if you remember the initial position of the knights, on 1 and 3, I had black knights, and on square 7 and 9, I had white knights. So that's what I've done. On vertex 1, I have kept a black circle, which is a black knight. On square 3, which also had a black knight, I have kept a black circle, which is a black knight. And on 7 and 9, I had white knight. So on vertex 7 and vertex 9, I have kept white circles, which are the white knights. So the vertices are the squares. Now the question is, how have I made all these lines connecting these vertices? The answer is that I have joined two squares or joined two vertices whenever a knight can move between them. So here in the previous diagram, I notice that if a knight is here on square 1, it can move to
If
square.
you make like a plus sign with all the others, then you can go ahead. Like, yeah.
Yeah. So if in an L shape, you can not necessarily a plus sign. Like if you're considering this, it will be a rectangle. It can move like this, or say it can move like this, or like this. So by a plus sign, you mean
No, the
this
last
one?
shape after you move all of them will be like a plus. Like if you move in between.
Let me see 1 second. The last shape where? Are you talking about the next slide?
No, like the last shape after you move all the knights in between two of them will be like a plus.
Okay.
And then from that you can like go to the end result.
Okay. So you're saying it will be possible in this case, right? Making this move.
Yeah.
Okay. So here, I know that I can move a knight from square 1. 1 second, I'll annotate it. Yeah. So I know I can move a knight from square 1 to square 8. And I know I can move a knight from square 1 to also square 6, because I can move 1 step down and 2 steps to the right. That's also an L. This is an L. So I can move from 1 to 6. I can move from 1 to 8. And no other L's are possible. Like if I make this L, you are again at 8. If I make this L, then I'm again at 6. So from 1, a knight can only move to 8 and to 6. So what I'll do is, I will join vertex 1 to vertex 6 and vertex 8. Yeah, so vertex 1 is joined to vertex 8 and to vertex 6. Because from square 1, a knight can go to square 6 and to square 8. Then I'll look at square 2. From square 2, a knight can move to square 7 in an L shape, or to square 9 in an L shape. And it can move to no other square. So I've connected circle 2, vertex 2 to vertex 9 and to vertex 7, because from 2 it can move to 9 and 7. And that way I have done for each of the vertices. I've seen where can the knight move from that square, to which other squares can it move. And if it can move from say square 3 to square 4, which it can, I join 3 and 4. But it cannot move from square 3 to square 5, because it has to move in an L shape, not in a V shape. It has to move 2 steps in one direction and 1 step in the other direction. So 3 to 5 is not possible. So I do not join 3 and 5. And that way I get a graph where the vertices are the squares on the 3x3 chessboard, and the lines are joined, like lines are added between two vertices if a knight can move from the first square to the other square. And if it can move from square 1 to square 8, it means it can also move from square 8 to square 1 by just retracing. That's also an L. So that's how I'm making the graph. Is the making the graph part clear to all of you? what the circles are in the graph, like the vertices are and what the lines in the graph are. The vertices are the squares in the chessboard, and the lines are the movement of the knight on the chessboard. It can move from 1 to 8. It can move from 1 to 6. It can move from 6 to 7 and so on. Okay, that is clear. And now we are out of time. We have 5 minutes left. So we'll look at it next time. Why? And here the graph I have made on the top, which is a cycle, is much less messier than this bottom graph. And it's exactly the same graph. I've just changed the positioning of the vertices. So 1 was connected to 8 and 6. Here also 1 is connected to 8 and 6. 2 was connected to 9 and 7. The same graph, I just redo it so that it looks less messy. Okay, is this part clear to you all? It's not a different graph. I just changed the position of the vertices so that it looks more cleaner, more neater. Okay, so someone has asked, can we move the black knight from square 3 to square 8? Yes, we can. It's an L shape. So I'll draw it. So if you are on square 3, you can move 1 step to the left and 2 steps below. Then you are from 3 to 8. So that's why I've joined vertex 3 and vertex 8, because you can move a knight from 3 to 8. Is it clear?
Yes, ma'am.
Okay, and is it clear to you all why these two graphs are the same? I've just changed
Yeah, they are the same.
They are the same. I just changed the position of the vertices. Instead of 1, 2, 3, 4, I've just positioned them as 1, 5, 6, 7. I changed the positions, but the lines are still between the same vertices. So say 4 is connected to 3 and 9. Even here 4 is connected to 3 and 9. And the knights are also placed on the same vertices. Black knights were on 1 and 3. Here also they are on 1 and 3. And white knights were on 7 and 9. Even here they are on 7 and 9. Now, I want you all to, this was the original positioning of the knights. In the new positioning, 7 and 9 had the black knights. So if we go back, 7 and 9 had the black knights and 1 and 3 had the white knights. So in the bottom graph that I have made, 7 and 9 have the black knights and 1 and 3 have the white knights. And I need to move from this graph to this graph by moving these knights. And where can the knights move? The knights can move along the lines, because the lines were representing knight movement. So from 1 to 8 it can go, which means when I say a knight can go from square 1 to square 8 on the graph, it means that it can go from this black knight, which is on 1, can go along this line to 8. And after this, it cannot go to 3 immediately. Like you cannot have this knight over here because there is already a knight here. And at a time on a square, you can have just one knight. Two knights cannot sit on the same square. So once you move the knight from 1 to 8, you cannot immediately move it to 3. But if you shift the knight on 3, you take it to the next square, you take it to square 4, then this space will be empty. Then you can move this knight to this square. And you want to make these movements of these black circles and white circles, which are the knights, along these lines. Or you can make any possible movement as long as you're moving along the line. And you want to change the positioning to this new positioning. And the answer is that it is possible because you just need to move anti-clockwise 4 steps. So if I clear the drawings, 1 second. I just need to move anti-clockwise 4 steps. So if this white circle on 9 moves 4 steps anti-clockwise, 1, 2, 3, and finally over here 4. Then it will arrive at 1. So I will have a white knight here. If this one moves anti-clockwise 4 steps, it will arrive at 9. This one will arrive at 7. So in the end, I'll get this positioning, new one, which I wanted. So in this case, it is possible But again, like other problems in Guarini's problems, there are lots and lots of possibilities. So this change of position is not the only possibility. And I've asked another brain teaser on a new possibility. Instead of taking black to the bottom two and white to the top two, this is a new positioning. I have black along the one diagonal and whites along the other diagonal. Can this change in positioning be made? That's the second question. I want you all to try it in the same way. Okay, so it says it's not possible. I've written it down, but I want you all to argue on your own why will it be possible or why will it not be possible, and we'll look at it the next time. I'll be explaining it anyway. Why will it not be possible? But you can try it out at home, and you can also try out other possibilities for the telephone problem, or seeing which diagrams can be traced with a pencil, which cannot. Okay, and we'll look at that next time. And there is another thing that we'll be looking at next time. We'll be trying to use something that you have looked at before during the sessions. You all have done pigeonhole principle, right? You all have already covered it.
Yes.
Yes, ma'am.
Yes, ma'am.
So now we are going to get pigeonhole principle into graph theory, and we are going to do something very interesting, but that's for next time. So not now. And we'll also be looking at graph coloring next time. So the vertices in a graph can also be colored, and there are rules for the coloring, and there are lots of problems linked to graph coloring, some of which were unsolved for hundreds of years. And even if I give you the solution now, we will not understand it. Like they were solved over 150 years, 200 years. So it's that difficult an area. Although it seems simple, there are just vertices and colors. But there are also very interesting brain teasers which are accessible to us. So we look at brain teasers on graph coloring. We look at how pigeonhole principle can be incorporated into graph theory, and we look at the solution of this problem. Why is it not possible? Okay, we'll do this next time.
Okay, miss.
And does anyone have any questions? You can ask on whatever we did today. Yes. Like you can unmute and ask, or you can, if you're not comfortable with unmuting, you can type in the chat box. I'll wait for 5 to 10 minutes more. If any of you have doubts, you can ask. You can type in the chat box. You can unmute and ask. Else you can leave the meeting.
Thank you, ma'am. Bye, ma'am.
Thank you,
Bye.
ma'am.
Bye.
Thank you, ma'am. Bye, ma'am.
Ma'am,
Thank you, ma'am.
Bye.
ma'am,
Yeah.
you said this was not possible. What?
Oh, you're asking about the current slide, right? The slide in front of you.
Yes, ma'am.
Okay. So I'm saying that if I have a chessboard, 3x3 chessboard, and there is a black knight on square 1, black knight on square 3, white knight on square 7, and white knight on square 9. Okay, so this is my chessboard, and this is how my knights are positioned. I want to move the knights, and you understood how the knights move. They move in L shape. So this knight on
Yes, ma'am.
1 can move to 8, or it can move to 6 because it can move in L shape. Now I want to make the knights move, and in a sequence of moves, can I change the positioning of the knights to this new positioning, such that a black knight is on square 1, a white knight is on square 3. So it is changed now. Here there was a black one. Now I have a white one here. There is a white one on square 9, and there is a black one on square 9. So I want to change the positioning of the knights by any sequence of knight moves, like L shape moves. It's the same. You had understood the previous question, why it's possible.
Yes, ma'am.
Yeah, so it's the same question, just that the new positioning is different. In this
Ma'am.
question, yes.
Ma'am, I think, ma'am, question. We can shift black knight to the point, but we cannot shift the white knight to that point.
So now, okay, you are right. So this movement, this change of position is not possible. But when you are giving an argument in any area of mathematics, you'll have to write a proof. You all have done proofs before, no? You have looked at, I
Yes,
think,
ma'am.
induction,
Yes,
pigeonhole
ma'am.
principle, and lots of other things. So what are those things? They give a logical argument as to why is something possible or why is something not possible. So you need to write a logical argument showing why will this not be possible. Okay, and that can be done using graph theory, and we'll look at it at like the next time in the next session. Okay.
Okay, ma'am.
I'll
Thank you,
stay.
ma'am.
Bye. I'll stay for 5 more minutes. If any of you have any questions, you can type in the chat box or unmute and speak.
Thank you, ma'am.
Bye.
If no one has doubt, they can leave now. Do I end the session for all?
Yes, I think Neha, you can
Yeah.
end it.
Yeah. Okay. Yeah. Bye. Thank you. Bye.
Bye.